In this lecture, we will study capacitors. A capacitor is represented by a circuit symbol which looks like this. And when the two wires or the two lines are equal length, then this is called a non-polar capacitor. And if the symbol is shown in this way, where one is curved, whereas the other line is straight, this is called a polar capacitor. And the difference is that the polar capacitor has a preferred polarity. So the straight line should be connected at a high voltage. So that's why this is written as the positive. And the curved line will be connected to the negative or the lower voltage side. So if you are connecting this polar one in a circuit, so you will make sure that the positive terminal is at a higher voltage. So let's say you have 12 volts on this side, but you have 10 volts on this side. So the positive one should be connected to the high voltage side. The non-polar capacitor has no polarity, so you can connect it any way you want. You can flip it upside down and connect it in a circuit in any way you like. It will not make any difference. So therefore, we have these two different types of capacitors, and these are the symbols for them. A capacitor will be represented by the letter C, and the units are in farads. So a capacitor, for example, can be 1 microfarad. Micro is 10 to the minus 6, or for example, 1 millifarad, or 1 farad. 1 farad is a very high value of capacitance. Typically, we would be dealing with microfarads and millifarads. So far, we have been studying resistive circuits only, and we know that a resistor dissipates power. As we know from our previous lectures, if I have a resistor R, and if a current I flows through this resistor, then we will have power dissipation in the resistor, which will be V times I, or V squared divided by R, or so on. So we can calculate how much power will be wasted in a resistor in the form of heat. Capacitor, on the other hand, does not dissipate power. So a capacitor can store energy or power, and then it can be used later. So when we are storing energy in a capacitor, we will say that the capacitor is being charged. So we will charge a capacitor, and during that process, energy is actually being stored in the capacitor. Later on, if I have a charged capacitor and if I connect it to a circuit with resistors, then I can actually use that energy that was previously stored in a capacitor. So in today's lecture, we will try to understand how a capacitor works. All right, so now let's see what a capacitor is actually made of. So any two metals, for example, if these are two conductors, so this is a conductor and this is a conductor. So any two conductors, if they are separated from each other by a small distance, d, and this region that separates them does not conduct current. So it's a dielectric or an insulator. So this structure actually forms a capacitor. Okay. So now if I connect, let's say, one metal to the positive terminal of a battery and the other to the negative terminal of the battery, then this structure is a capacitor. And what will happen is that the positive terminal will make this conductor to be positively charged, and the negative terminal will become negatively charged, the conductor. And we will have some charge now. So now we have a charge stored on these two different conductors, and that's actually the energy stored in the capacitor. Now, if I remove my voltage source, then the structure will still retain the charge. So I have these two metal conductors. One is now positively charged and the other one is negatively charged, and they will retain the charge. Now, for instance, if I connect a resistor between the two conductors, then a current will flow. Positive charges will move from this metal conductor to the other one, and the current will flow I in this resistor R, which will heat up the resistor, and which will be the power dissipation in the resistor, which is I square R, which is also equal to V squared divided by R. So you see the energy that was stored in the capacitor now is actually being used to produce a current in the resistor. So by definition, any two conductors separated by a distance from each other will form a capacitor. However, we want, in many cases, we want the capacitance to be large. So you see, for this case, the capacitance C might be very small. It might be very small, and in many occasions, we would like to create a large capacitance, and therefore we would like to see how can we construct a structure that will produce a large capacitance. A very common capacitor is called a parallel plate capacitor, where we have two metal plates. So this is metal, and this is also metal. So we have these two metal plates. They have some surface area. So this one has an area A, and similarly, this metal plate has the same area, let's assume both of them have the same area to keep things simple. So we have two metal plates, and they have some area, and they are separated by a distance small d. It's a very small distance between the two metal conductors. Now, this structure is called a parallel plate capacitor. What we will typically do is that we will connect one plate to a positive terminal of a voltage source and the other one to a negative terminal of the voltage source. The capacitance of this structure, C, is given as epsilon times A divided by D. Here, epsilon is the property of the material. So the dielectric material here between the two plates, epsilon is the permittivity of this material. For air, epsilon is for air, epsilon is 8.854 times 10 to the minus 12, and the units are farad per meter. So now you can see that the capacitance C is totally dependent on the geometric structure. It has nothing to do with the circuit in which we are going to place our capacitor in. It is not dependent on the voltage source. It is not dependent on the current. It has nothing to do with the rest of the circuit. So the capacitance of a capacitor is completely determined by the dimensions of the structure, the area of the plate, the distance between the plates, and the material used between the plates. One important thing to notice here is that if we decrease D, you see, if we decrease D, so we bring the two metal plates closer and closer together, that will actually increase the capacitance C. So to get a large value of capacitance, we would like the two metal plates to be very close to each other. Also, if I want to increase the capacitance, I will need to use a larger area. So the metal plates should be large. And finally, if I want to increase the capacitance, I can use a material with high value of permittivity. So epsilon, the larger the epsilon, the more the capacitance. So now that we have some idea of what a capacitor looks like, let's see what will happen if I connect this capacitor to a voltage source. So let's say, imagine I have this parallel plate capacitor. I'm going to draw it quite large so we can explain a few things. So I have connected a capacitor to a voltage source Vs, and let's say this source is equal to 10 volts. Okay. And the distance between the plates is D, as before. That's the distance. Both plates has the same area A. Now, we will assume that initially this capacitor was not charged, which means there was no charge on any plates of the capacitor. So the voltage between the two plates of the capacitor will be 0. We will represent the voltage across the capacitor, Vc. We will represent it by the symbol Vc. And the current in this circuit again is, let's say, I. So the battery is producing a current which is charging the capacitor. So initially our voltage Vc will be equal to 0 volts because my capacitor is not charged. As soon as I connect the capacitor in this circuit, KVL will say that when I go around the loop, KVL will say that I have a voltage rise of 10 volts, but then the voltage drop is 0 because the capacitor is not charged. So, which is a contradiction. So what the supply will do, that it will try to produce a large amount of current, which will try to charge this capacitor very quickly. So what will happen is that as we are assuming, or as we will always assume that the current is conventional current, so the positive charges will be coming moving in this direction. So the positive charges will come out of, let's say, from the positive terminal of the battery, and they will move to the top plate. So they will charge the top plate. So positive charges will accumulate on the plate on the top. Now remember, the amount of current produced by a battery by the positive terminal of the battery must be the same as the amount of charge actually coming back to the negative terminal of the battery. So if the top terminal of the battery is producing this positive charge, which is going into the capacitor, the negative terminal of the battery will require that the same amount of charge must be terminating or must be coming back to the negative terminal of the battery. So therefore, the positive charges will come this way. So where is this positive charge coming from? And of course, this positive charge is actually coming from this lower metal plate of the capacitor. And this metal plate is a conductor, and it's neutral, of course. So if positive charge leaves this plate, which will mean that there is now a deficiency of positive charge, which will mean that the plate will now appear to be negatively charged. So what will happen is that the upper plate will acquire a positive charge, and the lower plate will acquire a negative charge. So now, because of this charge acquiring on the two plates of the capacitor, the voltage Vc of the capacitor will increase. Okay, and very soon Vc will increase so much that it will become equal to Vs. After some time, very short amount of time, let's say at T1, Vc will become equal to Vs, and now KVL will be satisfied. And when this happens, then the current will stop flowing in the circuit. Okay, because now the battery is trying to push the charge on the upper plate of the capacitor, but the capacitor upper plate has the same voltage as the battery. So it appears like we have two batteries of equal voltage, and therefore they are trying to produce current in opposite directions, and they cannot. So therefore, the current will now stop flowing in the circuit. So as soon as you place a capacitor in a circuit like this, the capacitor will charge, and now you have positive charges on the top plate, negative charges on the bottom plate. And when you have charge on a capacitor, it actually has stored energy, which we will see shortly how much this energy is. Another thing is that once you have these charges on the plates of the capacitor, the charge will actually produce something called an electric field. All right, so the electric field always starts from the positive charges and it terminates on the negative charges. So it will produce an electric field in between the plates of the capacitor. And the electric field actually gives rise to the voltage. Okay, so we will have the upper plate at a higher voltage and the lower plate at a lower voltage. And that voltage difference between the two is the voltage across the capacitor, which we are calling Vc. Now, the voltage across the capacitor, Vc, is actually equal to E times D. Okay, we are not going to go into the details of this at this time, but just for our information, the voltage across the capacitor is equal to the electric field times the distance d. So the larger the electric field, the larger we will have the voltage difference. Also, later we will see that this electric field is proportional to the amount of charge on the capacitor. So the more charge we have, the stronger the electric field will be. And the stronger the electric field, the higher the voltage between the two plates of the capacitor. So with this discussion, we now see that if I place a capacitor in a circuit where there is a voltage supply, the voltage supply will produce a current for a short duration of time, which will charge the capacitor. And once the capacitor is fully charged, the current in the circuit will become zero, which means that the capacitor will look like an open circuit, or it will look like something that has a very high resistance value, which we call open circuit. So therefore, most of the time we say that the capacitor is actually an open circuit to DC. It's not always open, it's open after the capacitor is charged. So initially there is a small current that flows in the capacitor, but that is for a very short duration of time. And once the capacitor is charged, then we can very safely treat it as an open circuit. So now let's see how much charge will produce how much voltage. So we have this one relation which says Q equals CV. Now Q here is the charge. So you see this positive charge on the plate, the total charge is Q, and this negative charge on the plate is also Q. So you see if Q is 1 coulomb on the upper plate, it will be 1 coulomb on the lower plate as well, except that they will have opposite charges. So we will have positive 1 coulomb on the top plate and negative 1 coulomb on the bottom plate. And the reason for that is the amount of current that is coming into the top plate is the same as the amount of current leaving the bottom plate. So both of them should have equal amount of total charge. All right, so we have this relation that Q equals CV. C is the capacitance of the capacitor. V is the voltage across the capacitor. Sometimes when there is confusion, I will write VC to distinguish it from other voltages. But in this case, we are just going to call it V instead of VC, but we know that this is the voltage across the capacitor. So the charge is proportional to the voltage. So you see, we say that the charge is proportional to voltage. If I increase the voltage, more current will flow. That will result in more charge on the upper plate and more charge on the bottom plate. So the charge is proportional to the voltage. And the constant of proportionality here is C. All right. So C is the capacitance, and we already saw that C depends on a few things, which is epsilon naught A divided by D, right? So this is C. All right, so this is the main equation from which we will derive the current and voltage relationship. Now let's differentiate this equation with respect to time. So we will differentiate this equation with respect to time. All right, so if I do that, I will have dq by dt equals d by dt of c times v. dq by dt, what is that? That is charge per unit time. And charge per unit time is actually current. So dq by dt is the current I. It should be equal to, now c is a constant. C does not change with time, so therefore I can take c out of the derivative, and I'll be left with dv by dt. So this is our equation that we were looking for, which relates current and voltage across a capacitor. Now this equation is very important. It is very important to understand this equation. Now the derivative of voltage with respect to time, let's say, for example, if I have a situation that is like this, that this is time and this is the voltage across the capacitor, and let's say the voltage looks like this, that this is 5 volts. So you see, the voltage across the capacitor is, let's say, 5 volt as a function of time, and here it looks like, you see, the voltage is not changing. So if I take any 2 points along the time, so let's say 1 second and 2 seconds, and if I see what's the voltage at those two times, then I will see that the voltage is actually 5 and 5. So in this case, my dV, the change in voltage, is actually 5 minus 5, which is 0 volt, and my dt, which is the change in time, is actually 2 minus 1, which is 1 second. So what it tells me that the rate of change of voltage with time, which is dV by dt, that's the rate of change of voltage with respect to time. Like, how is the voltage changing as the time changes? And you can see that this is dV is 0, dt is 1, so this is 0. So you see, a constant voltage is not changing with time. So therefore, the derivative of the voltage with respect to time will be 0. Okay, so if the voltage across my capacitor is a constant like this, then I know from the above equation that the current will be equal to C times dV by dt, which means C times 0, which means 0 ampere. So if the voltage across the capacitor is not changing with time, this means the current is 0 through the capacitor. There is no charge coming into the capacitor. There is no charge leaving the capacitor. Therefore, the current is 0. Okay. On the other hand, let's say if my voltage looks like this. This is time and this is voltage across the capacitor. And let's say 1 second, 2 seconds, 3 seconds, and so on. And let's assume that I have a voltage this much, a voltage this much, and I can draw a straight line between these 3 points. And assume that at 1 second, my voltage was 2 volts. At 2 seconds, my voltage was 4 volts. And at 3 seconds, my voltage was actually 6 volts, if I assume something like this. So now let's pick any 2 points, for example, 1 second and 2 seconds. So during this time, the change in voltage is 4 minus 2, right? So it's 4 minus 2, that is 2 volts. And during this time, the change in time is actually 2 minus 1, which is 1 second. So therefore, dv by dt is 2 divided by 1, which is 2. So now you see my voltage is changing 2 volts every second. This is what this equation is telling me. It is telling me every second the voltage is increasing by 2 volts. And you can see from the graph that the voltage is actually increasing 2 volts every second. So let's say that this is the voltage across the capacitor. So I have a situation in which I have a capacitor like this, and the voltage we see across the capacitor is changing this way. Then according to my equation 1, which relates the current and voltage, I can now find the current, that the current is actually C times dV by dt, which says it is C times 2, which is, we can say 2C ampere. So this is the amount of current that must be flowing into the capacitor. So the direction of I is this way. So this current 2C, this much amount of current has to flow in this circuit to cause the voltage of the capacitor to increase linearly like this. So now you can see that the voltage across the capacitor will increase only if the current flows into the capacitor. Okay. So based on this, I can say that the capacitor acts like a bucket. Okay, so let's assume this is a bucket and you are pouring water into this bucket. So this is water. And when you are pouring water into this bucket, you have this level of water. Okay, and this is all filled with water. Now, water actually, for us, water will represent current. Okay, and this level, the surface of the water, will represent the voltage across the capacitor VC. So now you can think of what's happening is that if you don't pour any water, so means current is zero, therefore the voltage level will not move. It will remain the same as we saw over here. So you see when the voltage level remains the same constant, the current is actually zero. On the other hand, if a current flows into the bucket, okay, so you see the direction of current is important. So if the current flows into the bucket or water flows into the bucket, the voltage level will rise because the water level will rise in the bucket. Another thing is that you see the larger bucket actually means large capacitance. Whereas if a capacitor has small C, so you see this will be a smaller bucket, and it will mean you have a smaller value of C. So this is a bucket where you pour water or current I, and the level will rise very rapidly. If the C is small or the bucket size is small, the water level will rise very rapidly. Whereas if you have a larger bucket, which means you have a larger value of C, you will need a lot more current to increase the value of the voltage we see. Okay. Now this can be seen from the equation here. Okay. So you see from here, or maybe from here, we can see if C is large, so we got this equation by assuming that the voltage is increasing by 2 volts every second, okay? So the rate of change of voltage is constant. So the voltage is increasing 2 volts every second. Now for that to happen, the current must be equal to 2C. Now this tells us the difference between the larger bucket and the smaller bucket. If C is large, which is the larger bucket, if C is large, I will need a high value of current. Okay, I will need more water to produce a change of 2 volts per second over here. Whereas if I have a smaller bucket, then a small current will actually be needed. So you can see the similarity between a bucket and a capacitor. Now let's go back to our equation 1. Our equation 1 was saying that the current through a capacitor is equal to C times rate of change of voltage. Now let's imagine a different case. Here now I'm going to imagine that, let's say this is time and the voltage across the capacitor is here, and time, let's choose time 1, 2, 3, three different points on the time axis, and at 1 second the voltage is, let's say, 6 volts. At 2 seconds the voltage is 4 volts, and at 3 seconds the voltage is, let's say, 2 volts. So now you see the voltage across the capacitor is actually decreasing with time, okay? And in this case, my dV between, let's say, 0.1 and 2 is 4 minus 6. Okay, so that's minus 2. Now you would say that why did I choose 4 minus 6? Why I didn't choose 6 minus 4? So the convention is that we always choose the point which is at a higher time, so the later time. So the later time minus um, the earlier time. So for example, like 2 seconds minus 1 second. So the voltage is actually decreasing with time, and dt here is 2 minus 1. So again, you see, I will choose the later time first and the earlier time later. So it's 2 minus 1. And at time 2 seconds, the voltage was 4. So therefore, it was 4 minus 6. All right. So we have to be consistent. So that is 1. Dt is 1 second. So now you can see that dV by dt, the rate of change of voltage, is negative 2. Okay. So now we see that the voltage across the capacitor is actually decreasing with time. With this dV by dt, the current through the capacitor must be equal to C times negative 2, which will be negative 2C. So this is my current through the capacitor now. So you see the current is now negative, okay? So the current is negative. What it means is that I have a capacitor which was charged to some value, and my initial voltage was, let's say at t equals to 1 second, it was 6 volts. So I had 6 volts over here, and now the current that flows as the time increases, this voltage is decreasing, and therefore the current is actually flowing in the opposite direction. The current is now negative. So our positive direction will always be the direction that the current actually flows into the capacitor, like shown over here. So the current is flowing into the capacitor. But if the current turns out to be negative, this means that the current is actually coming out of the capacitor. So the positive charges are leaving this plate, and then positive charges are coming into this plate. So when the positive charges are coming into the bottom plate, they are neutralizing the negative charges. So the net negative charge becomes less and less with time. And when the positive charges are leaving the top plate, the positive charge, the net positive charge on the top plate is decreasing with time. So therefore, the voltage between the two plates of the capacitor is also decreasing, as we see over here, and therefore the current is actually coming out of the capacitor. And this process is called discharging a capacitor. So we are discharging a capacitor. So what is happening is that the energy that was stored in the capacitor, now we are using that energy to do some work in some external circuit. So the capacitor is being discharged over here. Now let's go back to the original equation where we had that I is equal to C times dV by dt. We would like to write this equation slightly differently so that we can get the voltage if we know the current, because this equation actually gives me the current if I know the voltage. So now I want to write it in a way that I can find the voltage if I know the current. So to do that, I will write it this way, that I will say that dV by dt is actually equal to I divided by C. And now if I integrate both sides with respect to time, I will get dV by dt. I will integrate with respect to time. And the other side, I will also integrate with respect to time. Okay. Now, instead of using the indefinite integral, let's say that I will assume that everything starts at t equals to 0. So let's assume starting time to be 0, and the current time is, let's say, t. So starting time 0, the current time t. And because I'm using t as my upper limit, so therefore I will change the derivative dt by d tau. And similarly, I will change here by d tau. Okay, so now I can say that my left-hand side is actually dv from starting time to the current time. And the right-hand side, because c is a constant, so I can take it out, and I will have integral of I from t equals to 0 to the present time. The left-hand side, I have a constant, which is 1 over here. So the integral of a constant is, with respect to v, is v itself. And then I will apply the limits from 0 to t. And the right-hand side would be 1 over c, integral from 0 to t of I d tau. If I apply the limits on the left-hand side, I will get the voltage at the upper limit time, which is the current time, minus the voltage at time t equals to 0 is 1 over c integral of I 0 to t d tau. And finally, I can write it as the voltage at current time is equal to 1 over c integral of I and plus the voltage at time t equals to 0. So this would be my general equation to write the voltage across the capacitor if I know the current through the capacitor. And this number over here, this is the initial voltage. So we say that this is the initial condition, that how much was the voltage across the capacitor before we started charging it. Most of the time, we can say that the capacitor was initially uncharged or discharged. So we can safely simplify the equation by saying that the voltage at time t0 was actually 0. And then the equation would be slightly simpler. So if I say that the voltage at 0 was equal to 0, so the capacitor was not charged initially, so therefore the voltage at any time t now, so the voltage at any time is actually equal to 1 over c integral of I dt. This would be a simplified version of the above equation where we are assuming that the capacitor was not charged initially. Okay, so now, so you can see that, let's call this equation 2, that equation 1. So we can now see that equation 1, of course, if I differentiate the voltage, I will get the current. And in equation 2 says that if I integrate the current, I will get the voltage. So now you can see that derivatives and integrals are involved when we are dealing with capacitors. Okay, so the capacitor is not as so the relation between the current and voltage of a capacitor is not as simple as it was in a resistor. Now let's say what equation 2 is going to tell us. So I want to first assume that what will happen to the voltage if I have a current that is constant with time. So let's say I have this current I that is flowing into the capacitor, and it's a positive current, and it's constant. Let's say at some value equal to I naught. I naught can be 1 ampere, 0.5 ampere, so on, whatever. It's just a constant value. It doesn't change with time. So if this is my current into the capacitor, so in the circuit it would look like this, that I have a capacitor and the current I naught, a constant value of current I naught, is flowing into the capacitor. Now you can assume that what will happen is that the charge on the capacitor will grow with time. So the charge will keep on increasing because the current is actually flow of charge. So all this current is actually coming on the top plate and leaving the bottom plate of the capacitor. And you can also think of this capacitor as being a bucket now. So where you have this voltage level and you are pouring water into it. And you know what will happen is that this water level will keep on rising. Okay, we are flowing water into it. So the water level will rise, which means the voltage across the capacitor we see should increase. So now let's see what equation 2 is going to tell me. So according to equation 2, the voltage across the capacitor, Vc, is equal to 1 over c times the integral of current, and my current is now constant I naught dt, and this is I naught is constant, so I will take it out of the integral, and you see that the integral of a constant would be t. Okay, so you see the voltage across the capacitor is now a constant number, I naught divided by c, and it depends on time. So at time t equals to 0, the voltage will be 0, and as time increases, the voltage will actually increase. So if this is time, then the voltage will increase like this. So this is the voltage across the capacitor if there is a constant current flowing into the capacitor. So the capacitor voltage will keep on increasing, as we can see here, the rate with which the voltage is increasing. So now let me just draw two different lines. So for example, this line and this line, both of them can represent the increase of voltage. But I would say that this line represents the case where C is large. Okay, so you have a large bucket. Okay, so if you have a large bucket and a constant current I naught flows into the bucket, then the voltage will rise slowly. Okay, so and you can see here a larger value of C would produce a smaller increase in V. And therefore, this is the this line represents the case where C is small. Okay, so the value of C will actually determine how quickly the voltage across the capacitor will rise. Now I want to discuss one more thing. From our main equation, I equals to C times dV by dt. I'm writing this equation many times because this is an important equation, and I want you to become very comfortable with it as soon as you can, actually, and to understand all the details of this equation. Now, one more thing that I want to discuss here is that what is actually the meaning that the voltage and current are related to each other, but one is obtained by taking the derivative of the other. And this has very important consequences later on when we will go and study the AC circuits. Although in this video we are studying the DC circuits, but I just wanted to make one point so that you are more prepared for what is about to come in the future. Let's assume that the voltage across the capacitor has a sinusoidal form. Okay, so let's say the voltage across the capacitor is actually equal to some constant, let's say V naught. So this is a constant. V naught can be 1 volt, 2 volts, whatever. And it is changing sinusoidally with time. So it's sine of omega t. So this is the voltage across the capacitor. Okay, so this is the voltage here. Now, if the voltage across the capacitor is changing sinusoidally, I want to see what will happen to the current. Omega here is the radian frequency, and we know that omega is 2 pi f. F is the frequency in hertz. Omega is the frequency in radians per second. Okay. If this is my voltage, then according to the equation, I can find the current I, which will be equal to C times the derivative of V naught sine of omega t. All right. And V naught is a constant, so I will take it out of the derivative. So I will have V naught times C, and the derivative of sine is cos. So I will have cos of omega t, and then the derivative of omega t is omega. So this will be multiplied by omega. So therefore, the current I is V naught omega C cos of omega t. This would be my current. This would be the current actually that is flowing in the circuit. And now I want you to pay attention to these two quantities. So you see the voltage is sinusoidal, so it's a sine wave, sine of omega t, and the current that will be flowing in the circuit will have a cosine form. Okay, now let's quickly plot these two to see what we mean by that. So this is time, and let's say this is pi by 2. Well, I'm not going to write it now. So let's say this is time, and I have pi by 2 over here, pi, 3 pi by 2, 2 pi, and so on. So first, let me draw the voltage, which is V naught sine of omega t. So the sine function will start from a 0. It will reach a maximum at pi by 2, and then it will become 0. Then it will reach a minimum, and then 0, and so on. So this will be my voltage. Okay, this is the voltage, which is a sine of omega t, and the peak value is V naught. Okay, now the current will be V naught omega c cos of omega t. So depending on the capacitance, let's say C is equal to 1 farad to make it simple, and let's say omega is equal to 1 radian per second. So therefore omega c will be 1, and my current will have the same amplitude as the voltage, so I can draw it more easily. Now the current will have a cos waveform. Okay, the current will be cos, and cos of 0 is actually the maximum, so this would be my starting point, and cos of 90 is here, and then I will have this kind of waveform. Okay, so this is my voltage V, and this is my current I in the circuit. And you notice something very important is that the voltage and the current are 90 degrees out of phase. So we say they are 90 degrees out of phase. Okay, we will discuss this in more detail once we go to the AC circuits, but for now, the voltage and the current are not at the same time. So you see, what it means is that when the voltage is at its peak, which is this point, when the voltage is at its peak, the current is zero. And when the voltage is zero, the current has its either the positive peak or the negative peak. So we can see all these points. This is, of course, pi by 2, this point. This point is pi. This point is 3 pi by 2. And here we have 2 pi. So 2 pi is one full cycle, so going from 0 to 2 pi. And after that, the waveforms will just repeat themselves. The voltage is lagging the current. Okay, in this diagram, you can see that the voltage is lagging the current. By this, we mean that the current will reach its peak value before the voltage does. So you see in time, the current reaches its peak value at t equals to 0, where the voltage reaches at peak value at some later time, which is over here. So you see the voltage is actually behind the current. So we say the voltage is lagging the current by 90 degrees. All right, so we will come back to this topic in our future video. For now, let's go back to the DC circuits. And one more thing that we want to discuss is the power or energy stored in a capacitor. Now we remember that power is the product of V and I. Okay, and we said I in a capacitor is actually equal to C times dV by dt. That's the current in a capacitor. So therefore, the power in a capacitor is V times C times dV by dt. So that's the power. Now we are interested in how much energy is stored in a capacitor. Now to find the energy, I will represent energy by E. Energy is equal to the integral of power, because you know that power is actually energy per unit time, so it is dE by dt, the amount of energy per unit time. That's power. So therefore, if I want to find energy, I will integrate this equation and I will get energy is equal to the integral of the power. Okay. So therefore, to find energy, I will take the integral of power with respect to time, and which will be the integral of this part. So I will have integral of V times C times dV by dt with respect to time. And I can see that now I can say that the energy is equal to, C is a constant, is equal to V times dV. And the integral of V with respect to V should be equal to V squared divided by 2. Therefore, we can say that the energy stored in a capacitor is half CV squared. This is the amount of energy, and the units should be joules. This is the amount of energy stored in a capacitor. We can also write this slightly differently, because we know that Q equals CV, or I can say that V is equal to Q divided by C. Therefore, V square is actually Q square divided by C square. So if I put V square, if I replace V square with this quantity, I can say that the energy is half C times Q square divided by C square, which is half Q square divided by C. So the energy can be calculated this way if I know the charge, or the energy can be calculated this way if I know the voltage. So two different ways of writing the energies. So this is it for this lecture. We will discuss capacitor a little bit more in the next video. I hope you enjoyed the lecture. If so, please subscribe to my channel. I'll see you guys next time. Bye for now.